Hello, everyone. My name is Amir Meisami, and I'm a research scientist at Adobe. Today, briefly and at a high level, I'm going to talk about the research that we have been working on for the past couple of years. That is the intersection of causality and sequential decision making with applications in digital marketing. I'm going to start by motivating the importance of causality in decision making in general and in sequential decision making in particular. Then I will cover the research that we have been progressively working on at Adobe, that is, formalism of bandits with causal knowledge, the relaxation of the problem when we do not have access to the causal graph, and further, the expansion of the idea to MDPs. Motivating the importance of causality in decision making is actually quite trivial, as the concept of cause and effect is the basis of how we get by as human beings. Causality improves our understanding of the environment, and it also helps us perform more efficiently. In decision theory, we perform decision making through maximization of utility. We evaluate this utility by calculating the expectation through probabilities of possible outcomes of these options. In causal decision theory, though, we can enable this dependence to be causal rather than just being evidential or associational. And that can consequently help us predict the outcomes of different actions in a much better way. And also, it will help us understand the effective intervention in a more meaningful manner. Similarly, in sequential setting, as we explore the environment to establish a better understanding of the reward system, causal knowledge can guide our exploration and enable a much more efficient procedure. Although in conventional setting, actions are normally considered independent, in more general cases, we assume some non-trivial dependencies among actions. And we already know that causal graphs can deliver excellent summarization of complex dependency structures. So the question is, why don't we exploit such side information that is often available in terms of domain knowledge or through some analytical methods? Regret and sample complexity necessarily scale with the number of actions. And a natural approach to deal with the large number of interventions is just to exploit the relationships between the way different interventions affect the outcome. We particularly focus on causal relations among interventions, and we use causal graphs to represent relationships between interacting variables in a complex system. We focus on a problem that is using previously acquired knowledge about the causal graph structure to quickly learn good interventions sequentially. The problem of interest here is email marketing or email campaign, where the overall target is to maximize the user interaction with the emails that could be defined as opening an email, clicking on a link, or eventually buying a product. To achieve these goals, marketers adjust several variables. For example, they may know that the length of the subject or the template or the time of the day to send an email can potentially affect the way the recipient is going to interact with that email. So it's quite important for them to find the right combination. As for the setting of our problem, we consider arms to be defined by intervention. For example, we can have a do operator where you can assign the product and also the send out time. Also, you can define certain empty interventions that is technically doing nothing. Also, for the features that we are not performing any interventions on. We just randomly generate a realization from their underlying distribution. As you can imagine, given the exponential number of options that we have for each of these variables, the number of manipulable variables, they can be quite large. On this graph, you are observing the causal structure for the email marketing campaign. It's of course the simplified version of it, where the reward variable is binary, that is whether the commercial link inside the email is going to be clicked or not. Features under control are the product, that is Photoshop, Acrobat, Adobe Stock, etc. Also, the purpose of the email, which could be for awareness, promotion, operations, and so on. So, also we have the send out time that includes morning, afternoon, and evening. Uh, Even so, these features are highly correlated with the reward variable. They are not the direct causes. The variables that are actually causing the clicks are the subject length, email templates, and send out times. So we're going to set these variables as rewards parents. And consequently, we are going to see the three features in blue that can be intervened to be connected with the rewards parents variables. Without causal knowledge, UCB algorithms generally update the confidence interval of the reward mean for each arm, and at each round, the learner chooses the arm with the highest upper confidence bound value. However, thanks to the causal graph structures, we are now able to make use of the expectation decomposition formula and benefit from certain term reductions. At every round, we only update the reward mean and upper confidence bound for every possible value assignment on only rewards parents variables. Similarly, we can show, similar to UCB algorithms, the, the Thompson sampling algorithms can also benefit greatly from the incorporation of causal information by reducing the exploration space. Here we have the numerical results of our simulation. We compare the performance of conventional UCB with causal UCB and Thompson sampling with causal Thompson sampling. The plot here shows the average regret over 20 simulations, just to have an approximate expected cumulative regret. Uh, for and Clearly, both causal UCB and causal Thompson sampling outperforms the conventional methods. Besides, we can observe that Thompson sampling algorithms generally outperform UCB algorithms, which is consistent with the literature. Now we move to a relaxed version of the problem. Uh, all existing works rely on a restrictive and impractical assumption that the learner is given full knowledge of the causal graph structure upfront. Here we develop a novel causal bandit algorithm without knowledge of the causal graph. Our algorithm works well for causal trees and the general class of causal graphs. The reward variable here is real valued, and for simplicity, we assume the reward is only directly influenced by one of the variables, which we call the reward generating variable, and on the graph is noted by XR. We don't know the graph structure, but we can obtain an equivalent class of graphs, known as the essential graph, by observational data. We can then identify the reward generating variable by interventions. And finally, we apply standard multi-arm bandit algorithms on interventions over the reward generating variable or a subset of variables that contain the reward generating variable. We design an algorithm that is known as central node UCB that simultaneously exploits the reward signal and the tree structure. And it does it to efficiently find the direct cause of the reward and then applies the UCB algorithm on a reduced intervention set that is corresponding to the direct causes of the reward. We also show that the results can be extended to a more general class of graphs. Our method contains three main stages, as you can see on this visualization of the tree graph structure. There is no V structure in a directed tree. So the essential graph obtained from observational data is just a tree skeleton, and we take it as our input. In the first stage, we find a directed subtree that contains the value generating the value generating variable, uh, the reward generating variable by performing interventions on the central node. That could change over time. In the second stage, we find the reward generating node by central node interventions. We also prove that the reward generating node can be identified correctly with high probability from the first two stages. So for the last stage, we are just gonna use a UCB algorithm on the reduced intervention set. We can also extend the idea to reinforcement learning, where similar to bandits, the regret or sample complexity bounds all scale with the number of states and also actions, which can be quite large in practice. Again, going back to the problem of interest, marketers adjust several variables in order to improve the likelihood of customers buying products. Customer in different dynamic states such as loyalty levels, willingness to shop, and also different intrinsic states such as gender, age, and purchasing power, they behave differently after receiving commercial emails. And we need to understand that dynamics. Here we revisit the original idea. The relations among different types of variables in the system can be represented by a causal graph. When we have prior causal knowledge, we do not need to treat all interventions independently, as normally standard reinforcement learning approaches do. We can instead only explore the low dimensional key variables in order to reduce the amount of exploration. Plus, we can deal with high dimensionality problem by incorporating low dimensional structures such as causal factored MDPs and causal linear MDPs. On this slide, I'm showing the reward causal graph on the left and the state transition causal graph on the right at this state for the digital marketing problem. In each graph, all variables can be categorized in three layers. The outcome variable on top layer corresponds to the green node, that is the reward variable and the state variable. The manipulable variables regarding to emails on bottom layer are in blue, and direct parent variables of the outcome variable are marked in orange. Uh, and we also use gray arrows to describe the complex the causal relationships between any connected two layers. At any time, at any stage, marketers adjust the blue nodes and they passively observe the values of nodes in orange and green uh, in the subsequent stages. We show that our causal MDP algorithms only require the knowledge of the identity of the manipulable variables, the outcome variables, and their corresponding direct parents. And we do not require the knowledge of the entire causal structures, including all the edges. We also show some numerical results for our approach on reinforcement learning setup. Uh, as you can see, as we increase the number of interventions, the regret curves show that performance of the causal methods, that is the causal UCB value iteration and the causal factored UCB value iteration are stable. The other two algorithms incur higher regrets when the intervention size becomes bigger. On the right, we now fix the number of parent nodes to be just three, while we change the range of non-parent variables from two to six. The number of interventions increases exponentially as we increase the number of non-parent variables. However, the number of parent variables value assignments does not change at all. For each algorithm here, the cumulative regret is calculated after 5,000 episodes and averaged over 10 simulations. And as you can see, uh, the causal methods are performing much more stable than the conventional algorithms. And with that, I conclude my talk. Thank you for your time, and I look forward to your questions.